This video is looking at how do we go from our high-level code, and this is some JavaScript code that we'd use in Khan Academy, to our code that the machine can actually execute. We aren't going to take it all the way down to an instruction set machine code. Instead, we'll go to assembly code. So what assembly code looks like is something like this. We'll assume that our system has 8 registers for the CPU, and our addresses and numbers that we can refer to are up to 16-bit. So this higher value here is 2 to the 16 minus 1. And then this is our codes that will map one-to-one to an instruction set that the computer that we'd be mimicking would be able to execute. So we've got some storage in registers or addresses, some arithmetic and logical operations, and then some flow of control and bit manipulation. When we're looking at this, we'll also consider this is our CPU, so we have our control unit. We'll be basically doing that job ourselves manually. The arithmetic logic unit will be doing that job. The register unit, which contains registers, so we have 8 registers, and we'll track what's going in there, and the memory system. And we'll only be considered with a couple of addresses in here. We'll say that the value A will always use the address 100, and the value B will always use the address 200. This would be determined by the operating system when the program is running. So we'll make those choices now. So what do we need to do? First, we want to have a variable A. So we want to put in address 100 the value 10. So if we look at what we have for options, the only movement things we can do are load, store, or move. Well, we don't have anything in registers. We want to store something into an address. Okay, so we want store. We have to take a bit pattern found in register R. Well, we don't have anything in the registers yet. So first we'll need to put something in the register. We need to put a number. So we don't want to put something in an address, but we want to use this B load or bit load. Think of this as A load or address load. We want to load a particular number into some register. So let's take that, we'll load. We want to look at the syntax, and it's first the register, then the number. So first we'll say register 0, and we want to put the number 10. So what this does now is puts the value 10 into this register. And then we want to actually store this. So if we look at our pseudocode again, we'll store the value at some register into an address. Great. So we want to store the value at this register into this address. So what we want is this, and we say that by saying store the value at some register, oops, we're in register 0, into the address 100. This is now done, this first line. So if you think of this as a single command here, well, these map to 2 commands over here. We refer to the portion of memory here, this is our data for the program, but these instructions, which are then mapped to these instructions, these will have to be resident in the memory as well. So these will have addresses here. And you'll see that when we come up to the if statement. So more to follow on that part. We'll have to get our value for B stored the same way. That's going to end up in 200. So we'll have to do here, first we'll need to load it. We'll put it in address 1, correction, register 1, because it's not used yet. And we'll use the value 6. And then we'll store that value into address 200. So we end up with the value 6 here, and then this is stored in 200 over here. Well, next we come up to this if statement, and there's a lot of stuff going on here. So let's look at it like this. First, we're going to need to do our check over here, and then before we can evaluate this end, we need to do our test. Lost my control there for a second. We'll have to do our test over here. For this B is going to be less than 7. Then we can do check our end, and then we need to do something for our if statement. So we need to figure out, well, how can I do a comparison? And again, we'll want to check back and see, well, what are our options going to be for our assembly code. We don't want to change around contents. We don't want to do basic operations. We want to do a comparison. So we need to compare the value in one register with the value in another register. If the first value is less than the second value, we'll store the bit pattern 1, so 1 will mean true, in a third register. Otherwise, we'll store the bit pattern 0, false, in that same third register. So the way that we would write this would be, now we can say compare directly because we have our representation for A and B already in registers. Let's change there we go. We want to compare, let's get that out of the way so it doesn't mess things up. We want to compare the address, correction, register 0, because that's where A is, to register B, which is in register 1. And we'll store this in, we haven't used 2 yet, so we'll just store it in 2. Alright, when we execute this, we're checking, is register 0 less than register 1? 10 less than 6? No. So that means that we have to store 0 in register 2. We finish this. Now we move on to B less than 7. Well, we don't have a 7, so first we'll need to load it the same way we did with these initial numbers. So we'll load in register, we're not using 3 yet, so let's use 3. We'll load the number value 7. So when we execute this, we'll end up with the 7 there. Now we have our representation for B and for 7 both in registers, so we can do another comparison. We'll do compare between where B is, register 1, to where our 7 is, register 3, and we'll store that in, we haven't used 4 yet, so let's use 4. Is 6 less than 7? Yes, it is, so we'll store 1 in register 4 and look at the code for compare for that. Now that we have both operands for our end function, we can look at using AND. So we'll check our syntax for that. So AND we'll take A and B and we'll store the result in register R. So AND ABR. So we want AND. Now our result for A less than B was stored in register 2. So 2, B is less than 7 was stored in register 4. 4, and we'll store this in, well, let's store this one in 5. I'm choosing these arbitrarily. Compiler design would optimize which way that these would go. So we're taking 2 and 4, we'd fire those up to the ALU. 0 and 1 would give us a result of 0, so true and false is false. And this is stored in 5, so we store another 0 over here. Now gets to the tricky part. We need to do a, should pull up the code. We want to look at this. The only thing that's going to affect our flow of control is this jump command. So we want to do a jump to a piece of where the actual instructions are. So we want to go to this address for the instructions. If the bit pattern in the register that we provide is equal to the bit pattern in register 0. So the comparison in register 0 is always going to be the same. Otherwise, we just keep going with the next execution. So we're going to want to check to see if the result of this end function is true or false. If it's true, then we want to do these instructions. Otherwise, we'll jump with to the next instruction down here. So since we're going to be comparing to register 0, right now we don't have the value 1, which is what we want to ensure. So we'll have to load the value in register 0, the value 1. Now what happens here is this one gets replaced. So we no longer have that 10, and instead we have the value 1. Now we're able to say I want to jump if the register at the result of our last operation where we did the AND here was stored in register 5. So down here, if this is going to be equal to the content of register 0, we want to do something else. Otherwise, we'll carry on. Well, we don't know what we want to do else yet, so we'll have to leave that for now. So let's just leave some space. If we go to the end, we're done our program. So in this case, we would have to halt. Halt is the last command down here. It just means that we're done the program. Well, now if we want to say, well, where are we going to be jumping to? We need to look at what the actual addresses for these are going to be. So let's use green to say what our address numbers will be. For the program, this would be address 0, 1, 2, etc. So these are always going to be sequential. And that lets us know that, well, in this case, we would want to jump to address 11 to continue. In order to, now we're at this line, in order to do this, we want to perform 3 plus 4 and store it in A. So we want to do an addition operation. We check our table, so we need register values again, but we have numbers. So like we saw back here and here and here, we needed to first load those numbers into registers. So we can also overwrite what we'll be using. So let's store in register 0, we'll store the number 3. In register 1, we'll store the number 4. And then we'll say, and we'll take the content of register 0, the content of register 1, and we'll store that in register 2. So when we execute this, what we're doing is we're overwriting this 6, this 2, and this 1. Because when we execute this line, we store the value 3 in register 0. We store the value 4 in register 1. We add these together, the ALU would do this, and we get a result of 7, which we store in register 2. Now we get to the end here. There's nothing else to do for this block, except we haven't actually updated what we're going to have for address A. So in order to change that, we're going to have to look at, well, my address A was referring to address 100. Now how did I put it in initially? I had to use this store command. So I'll have to update that. We'll need to store the contents of register, we stored a result in 2, so register 2 into address 100. This will then update our program so that now the value of A is going to be 7, which is what the result of our calculation was. That hits the end of our if statement. So now we'd either want to jump back up to where we left the initial execution, or we could carry on. We'll just assume for simplicity that we'll carry on for this one and we're done. So we have halt again. And we'll add our last program values. So these are the addresses for where the program resides. So note from here that 1, 2, 3, 4 commands in a high-level language ended up translating to 15 commands in assembly. From the assembly code, each of these would go one-to-one when they are assembled or translated into the machine code, and it's the machine code that the computer would be able to run. This ends the video on the basics of compiling.